Hey folks, how's it going? This is Rob coming to you with a breakdown of midterm exam number 2 for Math 134. In this video, I'm going to go ahead and break down for you step by step how each of the problems are solved. So if this is something you struggle with, you can compare your answers to my answers. All right. Off the bat, I hope that I did see, solid note sheets being submitted. So it's good to see that that was at a maximum this semester. Good use of the note sheet. You want to really take advantage of that. And so the meat and potatoes is really going to come down to the optimization. A lot of the stuff could have been put on your note sheet except for that, but I'm definitely going to cover everything in detail. So number one is just a problem about cost, revenue, and profit. So we have Pulsar manufactured a series of 20-inch flat tube LCD TVs. The quantity X of those sets demanded each week is related to the wholesale price by the following equation. The weekly total cost incurred by Pulsar for producing the X sets is given by these equations. The cost equation. We need the revenue and the profit function. So first of all, we know that revenue is equal to the price times the quantity sold. All right, so in that case, we're going to take this and multiply it by x. So we get negative 0.006 x squared plus 180x. All right, the other thing we know is that profit is equal to revenue minus cost. So I essentially need to take the revenue and subtract the cost. Now you should put this in standard form, meaning a highest power of x first. So that would be, and this has 1, 2, 3, 4, 5. 2, 3, 4, 5 x cubed. So that's a like term. Now what I need to do is the second one. So I need to take minus 0.006 x squared and subtract minus point. So I'm going to do net 0.006 minus 0.02 or negative 0.02, because what you want to be doing is you're subtracting this many x squareds from that many x squareds. I'm going to do this on my calculator. So on my calculator, I'm typing negative 0.006 minus negative 0.02. And what I get when I do that is plus 0.014. Okay, and then I've got 180 minus 120. And then I've got 0 minus 60,000. Okay, and remember, this makes sense because remember what we talked about with profit function. What we know about profit function is that if you sell nothing and you make nothing and sell it, you're going to take the hit on the fixed costs. And that's what we know, right? Remember, the fixed costs are represented by the number that, if I make nothing, you still pay the fixed costs like rent, etc., utilities, right? Like if I take a 1 month vacation, I still have to pay the mortgage, right? That doesn't matter. But I don't have to pay as much, for example, electricity or water or heat. So those things would be variable costs, okay? In my particular scenario. So this is revenue and profit, okay? Now I need to find the marginal cost, the marginal revenue, and the marginal profit. And so we're told that these are essentially the derivatives. So so all we're going to do is apply the derivative laws. It's just now in context. So the derivative of the cost is, and remember there are 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Exponent comes down, 6, drops by 1. Okay, similar thing, 0, 4, x plus 120. Okay, revenue, marginal revenue, similar. Okay, don't forget the negative sign there. So negative 0.012x plus 180. And then finally, the marginal profit. And that is, oh, and I forgot. Silly me. Don't forget my 2 there. That's actually pretty important. Okay. Negative 0.12345 x squared plus 0.028x plus 60. And then remember the negative 60,000, that goes away because you're differentiating a constant. Okay, so I do apologize. I did forget to put that 2 in there. So hopefully you didn't stop the video and start freaking out and say what happened with the 2. My apologies, it should be there. Last step is we need to do P of 2000, P derivative of 2000, and interpret. So what that means is the derivative, the marginal profit at 2000, so that's what you get when you plug in 2000 okay, so I'm going to do that on my calculator. So we have negative 0.12345, and then you type your 6. Unfortunately, I don't have my TI calculator simulator anymore, so I'm kind of doing this in the background. Okay. So you might be able to hear me typing it in. And when you do that, what you get is 92. So you need to interpret your results in context. That was half the points. So the profit from producing and selling. So the marginal profit is telling us at this point in time, if we continue to make another of these TVs, what are we going to generate in profit? So you could see this as the 2001st TV is $92. Because at this point in time, remember, the derivative of anything tells you the change. So the derivative of the profit, i.e. the marginal profit, tells you at this point, how much am I making profit-wise from selling that additional TV? So when I'm at 2000, it's saying, how much additional profit am I making when I sell that next TV, that 2001st TV? If you're stuck on this stuff, I really recommend you go back and take a look at some of the stuff we did around. This is section 9.8. Remember, this wasn't assessed on the first midterm because we did it on the same day as the first midterm. So if you have any questions about this problem, please make sure you rewind and go through this again. But otherwise, I'm going to go ahead and I'm going to move on to the next problem. All right, this problem has to do, and I'll try to zoom in a little bit. This is first derivative applications. So these have to do, I'm just going to zoom out. Sorry about that, just a little bit. Okay. This is going to come from section 10.1. That was applications of the first derivative. So I need to know where this function is increasing and decreasing. Now, many of us did a very good job with this. You need to start by calculating the derivative because the derivative tells you where it's going up and down. So I've got, remember to use our quotient rule, low, d high, minus high, d low, over the bottom squared, and away we go. So that's why I really emphasize the fact that we need to understand these derivative rules because they continue to come back throughout the semester. So the derivative of 2t is 2. The derivative of t squared plus 1 is 2t. Okay, so if I do this distribution, what I get is distribute 2t squared plus 2 minus, so I do this, distribute the 2t to the 2t. So maybe I'll cross this out so it doesn't get too confusing. Minus 4t squared all over the original t squared plus 1 squared. So now what I want to do is I want to simplify. So when I simplify, these are like terms. So I get minus 2t squared plus 2 over t squared plus 1 squared, which is the same thing as negative 2 t squared minus 1 over t squared plus 1 squared. All right, so that's good at this point. So now I need to figure out any critical numbers. In other words, I need to figure out when is the derivative 0, because when the derivative is 0, that's the borderline between when we're increasing and we're decreasing, right? To have a positive derivative means we're increasing. To have a negative derivative means we're decreasing. To have a derivative of 0 means we're neither, right? We're in no person's land, so to speak. We'd also want to look for any critical numbers. Now I know there are none, and the reason is because t squared plus 1, there are no real numbers that make that 0. So all I'm going to do is focus on the top. So in other words, negative 2 times t squared minus 1 is equal to 0 when? Well, we can solve that. That's the same thing as t squared minus 1 equals 0. And so that either means t is 1 or t is negative 1. And so now we set up our sign diagram, but also, am I missing something? No. Okay. So as far as I know, we're in pretty good shape. So I would now need to go ahead and set up a sign diagram, right? Because the purpose of what we're doing here is we want to analyze this thing, right? So we want to set up our sign diagram because our sign diagram is going to let us definitively prove kind of what's what here. All right, now let's just do one last look through on this. So low d high minus high d low over the bottom squared, and away we go. Okay, so here's what I'm going to do. I'm going to put negative 1. Everything looks good to me. So I've got basically 3 intervals. What happens before negative 1, what happen, 3 intervals, right? Before negative 1, in between negative 1 and 1, and after 1. So I'm going to choose my test points right now. So I'm going to choose 0. I'm going to choose negative 2. I'm going to choose 2. So look, no matter what you plug in 0, you plug in 2, you plug in negative 2, the bottom is always positive because you're squaring it and it can't be 0. So what that means is if I plug it into the derivative, if the top is positive, we're good, it's positive. If it's negative, etc. So when I plug in negative 2, I get negative 2 squared, which is 4. 4 minus 1 is 3. 3 times negative 2 is negative 6, so that's a negative. 0 minus 1 is negative 1. Negative 1 times negative 2 is 2, so it's a positive. And 2 squared is the same thing as negative 2 squared. So you can see I'm also going to get 4 minus 1, so that will be negative. So my conclusion is we're increasing in one place from negative 1 to 1, and you really need to use soft brackets. I was lenient on this test, but it is important that you do that. And it's decreasing from 2 places, negative infinity to negative 1, and I put the u there, 1 to infinity, right? Because this is the place where the derivative is negative, or rather is positive, and this is the place where it's negative. Okay, so what I didn't see enough of, and this is just in the work that I've looked at so far, there was not enough of setting up sign diagrams. It's a really, really, really important step in solving these problems. Okay. So now we're going to find minima and maxima, and that is the very similar process. So we're going to take the derivative, we're going to set it 0, we're going to set up a sign diagram, and we're going to see where the sign of the derivative changes either from positive to negative or etc. So of course the first thing you need is the derivative, And the derivative here, you bring down the 4. 4 times a half is 2. And this becomes negative 2x. Okay, one thing I think we struggle with is taking out the greatest common factor. It's 2x. So this is x squared minus 1. So if this is equal to 0, right? Well, either x is 0, because 2 times 0 would be 0, and 0 times whatever is 0, or x squared minus 1 is 0. And we already know from the last problem that that suggests either x is 1 or x is negative 1. So now we use this to set up our sign diagram. Okay, so we have 0, we have 1, we have negative 1. Okay, my test points. I'm going to choose, and actually just make sure we put our positive 1 here and our negative 1 here. I'm going to choose negative 2. I'm going to choose 2. I'm going to choose, let's choose a half, negative a half, and a half. Okay, because we need to see what's the derivative before, what's the derivative after, and so on and so on. So, here we go. If I plug in negative 2, let's focus on this. What you'd get is this would become a negative, because 2 times negative 2 is a negative, like a negative 4. Negative 2 squared is 4. 4 minus 1 is 3. So we have a negative times a positive, which is a negative. So it's decreasing before negative 1. Okay, now we plug in negative a half. So 2 times negative a half is negative 1, so it's a negative. Negative a half squared is a positive a quarter, but because negative 1 is more than a quarter, it's going to drag it down, make it negative 3/4. So we have a negative times a negative, which is a positive. Okay, so that's a good sign. So it essentially was going down, then it started going back up. So that's a sign that this is going to be a minimum. Okay, so I'll erase. Okay, now I'm going to plug in positive a half. Well, positive a half, 2 times a half is 1. But then we get the same thing happening here, right? Because negative a half squared is a quarter, but so is positive a half. So you'd get a negative. So we'd get a positive times a negative, which is a negative. So now we are going up, and then we started going down. So we reached a maximum. Finally, let's plug in positive 2. So 2 times 2 is 4. That's positive. Okay, 2 squared is 4, minus 1 is 3. That's also positive. So it's a positive times a positive, which is a positive. Okay, so what we have here is we have a min, a max, and a min. So we have min at negative 1 comma something and 1 comma something. And we have a max at 0 comma. So to get what we need to plug in the points. So if I plug in 0, right, 0 to the 4th is 0, times a half is 0, and then minus 0 squared. So that's a maximum of 0. So it's going to hit a maximum, a peak at 0, and then start going back down. If I plug in 1, well, 1 to the 4th is 1. Half of 1 is 1. So it's basically a half minus, and then 1 squared is 1. So it's negative 1/2. That would be positive 1. And if I plug in negative 1, well, it doesn't matter, because negative 1 times negative 1 times negative 1 times negative 1, well, that's still 1. 1 times a half is a half, right? And then negative 1 times negative 1 is 1. So you actually end up getting the same thing. So we have a min, 2 mins, 1 negative 1/2, negative 1 negative 1/2, and a max at 0, 0. Now, we talked about this a little bit in class, but when you have what's called a quartic function, and it's called a quartic function because the biggest power of x is 4, also because the number in front of the 4th, the x to the 4th is positive, what you get is you get a function that looks something like this. That's generally how quartic functions tend to look, though it depends from function to function. So you can see that we have 2 mins and a max. So that kind of makes sense. I encourage you to graph this and check for yourself if you don't believe me. So go ahead and make sure you understood what I did here. And then in a second, I'll go ahead and I will move on to problem 3. Okay, so now problem 3, we're looking to second derivative applications. So second derivative applications means we're looking at section, that's a little bit weird. We're looking at section 10.2. You might have noticed that I left off curve sketching. There is no 10.3, and the reason I did that was because curve sketching is a very involved process. It involves calculating a lot, and ironically, so did the optimizations. But I figured, look, either I can have them spend a lot of time curve sketching or a lot of time optimizing, and so I went towards optimizing, personally. Okay, second derivative applications. So we need to find the inflection point. Now, here's the thing. I kind of tried to set you guys up. When I say the word second derivative, that should indicate that you're going to need the second derivative. All right, I might not be as nice on the final in terms of telling you what you need to know. So it's 12x minus 6 is the second derivative, and that's the same thing as 6 times 2x minus 1. Okay, and so you have to find what makes the second derivative 0. Obviously, 6 isn't going to make it 0. So basically, that's like solving 2x minus 1 is 0, which means 2x is 1, which means x is 1/2. Now, if you stop here, you're not getting full credit because you haven't given me a lot. So you've shown me that the inflection point is a half. X a half, that is to say, represents an inflection point. But you still need to set up a sign diagram to prove that it's an inflection point, because you don't know that the second derivative changes signs from the left to the right. And that's an important step of any inflection point based problem. So I'm going to choose 0 and plug it in, and I'm going to choose 1 and plug it in. It's very similar to what I did in problem 2. Okay, and we're plugging into the second derivative. So when I do 2 times 0, so this is always positive, right? So this will determine the sign. So 2 times 0 is 0. 0 minus 1 is negative 1. So that's negative. So we're concave down. Okay, and this is cubic, so I've got a sense that that's what's happening. Now I plug in 1. Well, 2 times 1 is 2. 2 minus 1 is 1. So here, we're like this. And so what any cubic function, when the biggest power of x is positive, they tend to look something like this, where you have this inflection point in the middle that represents where the graph changes from concave down to concave up. So that confirms, yes, 1/2 represents an inflection point. Now we have to plug it in because you do need to get the y. And I'll just shorthand 18 times 1/2 is 9. Okay, so I get 2 times 1/8 minus 3 times 1/4 plus 9 minus 8. And 2/8 is 1/4. So 1/4 minus 3/4, and then this is plus 1. So 1/4 minus 3/4, well, that's negative 2/4, or in other words, negative 1/2 plus 1, which is 1/2. Okay, so the conclusion is points of inflection, there is one, and it occurs at 1/2, 1/2. Okay, so in terms of credit, if you were able to do both derivatives, that's worth points, if you did them correctly. If you could make them 0 and find the x, that's worth some more points. If you plug it in and get the x and the y, that's also worth points. But you cannot get full credit unless you've given me some definitive proof that that is in fact a point of inflection. That's extremely important. You have to be able to tell me that, yes, I know it's a point of inflection because I can show you, Rob, that the sign of the second derivative changes as we cross over. That is to say, on the left, the sign of the second derivative is one thing, and then on the right, the sign of the derivative is the other thing. It's going to be a second derivative, that is to say. This is going to be very important because, again, where we're going longer term is we have to be able to remember this. but also moving forward to the final, I might not be telling you inflection, second derivative, sign diagrams. These are some important things to know. Okay, so please make sure you understood what I did here, and then when you're ready, I'm going to go ahead and move on to the next problem. Okay, so optimization. This was a very, very difficult problem. Now, I'm going to be straightforward and tell you this. I do, and I will likely be adjusting some grades. I will likely be adding some additional points. I do that every semester because honestly, I'm not going to sit here and tell you I'm a master of test design. I do feel that in the future, I am going to make the optimization worth less. I do think optimization is important, but so it's a couple things. Either I'll make it worth less or I'll rethink my problems here, because on one hand, I do want to give you challenging problems. But on the other hand, when I give you very challenging problems, the challenge is now it becomes a quarter of your grade. And I had a lot of people really kill it on 1, 2, 3, and 5, but then get undermined by 4, or maybe they spent a lot of time on 4, etc. So on my end, I'm going to make it change what it's worth. On your end, I would offer this as a strategy. I would suggest, and I'm going to tell you this from my college days, start by always looking through the entire test when you get a test. Look through each page first, see what you need to do. Then I would recommend don't do the hardest problem first. Do the easiest problem first. So if I was you, I would be doing the optimization last, because then I could do 1, 2, 3, and 5, clean those up, get the 135 easy, and then optimization, whatever, partial credit I can get is good. And if you can scrape a perfect score on the remainder of it, right? 135 out of 175, you'd have a 77% right there, which is solid. And then if you could scrape even 10 points out of this one, and I was pretty generous with this, you'd be over 80%. So I would just think about that. I'm always a believer in knock out the easiest problems first. 1, it builds up your confidence, like, yes, I can do this. 2, it secures the easy points, because what happens is if you get bogged down in the optimization, right? Well, what happens is then when we get to the point where, you spent so much time, then there's almost no time left. And then you miss the easy questions where you could have picked up the points. All right. So inventory control and planning is the first, and you only need to choose one. Now, someone said to me that I had apparently said not to worry about inventory control and planning for the midterm. So anyone who did choose this problem, I did take that into account, and I was very generous with how I awarded credit on this problem. And that's only because I didn't say it. Now, you might say, Rob, that's not really fair, right? Because, if I chose the other one. But here's the thing. The other one is a lot more straightforward to do. So if you said, hey, Rob, I don't know how to do inventory control and planning, fine. Do the storing radioactive waste problem instead. Okay? So Rockin' Rob's radical rutabaga reduction is a smash hit in the Boston area. As a result, Rockin' Rob plans on bottling and selling 2 million, jars this year. The bottles are ordered from Big Ben's Bottleporium. Each shipment of bottles costs $200, and each bottle costs 40 cents per year to store in Rockin' Rob's warehouse. How many orders of jars should Rockin' Rob place per year, and how many bottles should be in each shipment to minimize the ordering and storage costs? Assume that each order contains the same number of jars, we'll call it X, and that the entire shipment is used up before the next shipment arrives. I recommend, if this is a difficult concept for you, take a look back, because I believe we're on the point where we're on. This is 10.5. 10.4 was just doing the extreme value theorem. There is an inventory control planning with motorcycles that we did as well. Okay. So if we have X bottles, so every order contains X jars or bottles or whatever you want to call it. So basically, if I have 2 million jars that I'm going to order in a particular year, and I divide by the number of jars per order, well, that's going to tell me the total number of orders. So equals number of orders, right? So for example, if I have 1,000,000 jars per order, I'm going to need 2 orders, right? 2 million divided by 1,000,000. If I was to do 500,000 bottles per order, I would need 4 orders. 2 million divided by 500,000. So you can see how that might work there. Okay? So what I know is a couple other things. I know that it's $200 per order in shipping costs, and that's a flat fee. So that is helpful to me because the more orders I place, the more shipping I'm going to incur. If I place literally 2 million orders of 1 bottle each, that's not good because I'm going to have to pay 200, right? 2 million times. That's not going to be ideal. Also remember that X over 2 represents the average bottles in the warehouse. Okay, because we know that the entire shipment is used up before the next shipment arrives. So at any given time, if we buy X jars, right, the number of jars in the warehouse is going to be fluctuating between a maximum of X when we just got it to 0 when we run out. So we do the X divided by 2 to indicate the average. Okay. So here's where we go from here. I now need to figure out where I'm going towards is I'm going towards a cost function. So I need a couple things. The first thing I need to know is what are my shipping costs going to be? So the shipping costs are going to be given by in any given year. Well, I'm going to take the total number of orders and I'm going to multiply it by the cost per order, right? So if that's my orders times the cost per order, right? That gets me this right here, and that's going to be my total cost of shipping. Total cost. So you can see that the more bottles I buy, the less I pay for shipping. If I buy 1 bottle per order, I'm paying $400 million to ship in a given year. Okay? If you think about it, if I'm bottling some kind of rutabaga reduction, that's bad, right? I don't know if you've ever sold $400 million of anything. That's not easy in a year, right? That's not easy. Many companies don't do that. So buying 1 bottle at a time, not what we want to do. You can already see it's going to be astronomically expensive. Then I need to look at the shipping cost. So it costs me 40 cents per bottle to store per year. And I'm also going to need to take that and multiply it by X over 2 because that's the average number of bottles. And what that gets me is 0.20x. And so if I want to know my costs, well, these are my costs, right? The shipping plus the storage. Okay, so what I'm going to do is this. Let's define our cost function. So the cost associated with x is equal to 0.20x, the storage plus the shipping. 400 million over x. Okay? So now we're optimizing this. And so in optimizing, what we want to do is we want to do the derivative. So that is 0.20. Okay, now this derivative, remember, this is x to the negative 1. So you bring down the negative 1. That turns the plus to a minus. And then you drop the x to an x squared. Okay, now another way to write this one would be 0.20 x squared, right? Because I'm just going to multiply this by x squared over x squared. I want to pull this together over one denominator. Okay. And now I'm going to do what makes this 0? What are the critical numbers? So one of the critical numbers we can see right away is 0. I'm sorry, I'm just going to move this down. One of the critical numbers we can see immediately is 0, because if you plug in 0, right, well, you're going to have an undefined denominator, right? This is going to be bad. Denominator 0, it's undefined. Now, fortunately, 0 doesn't really make sense in this context. It is part of the implied domain, right? Because we can't order less than 0. There's no such thing as negative bottles, but we can't order more than 2 million because that's the total number we're supposed to order for the year. But in any case, 0 is not a critical number we're going to consider. What we're going to do is we're going to set the numerator to 0. And then we'll solve. So we'll add 400 million, and so this is supposed to be x squared. We'll add 400, 2, 3, 4, 5, equals 0.2 x squared. We'll divide by 0.20. So when we divide by 0.20, it actually becomes a very big number. What we get is 2 billion. And then we take the square root. Now, this could be a positive or a negative, right? Because when you solve for x and you need to take a square root, and we're taking the square root of a positive, we're going to get a plus and a minus. So what we get is we technically get plus or minus 49721 approximately. And I would have been flexible with how you rounded this. It's plus or minus, but obviously you can't order negative 50,000 bottles, so the negative is out. So that essentially leaves three numbers to consider if we're looking for an absolute max. I'll do this in black. 0, 49,721, and 2 million, right? So in other words, we could order nothing, and that isn't really feasible in this situation. We could order all the bottles in one shipment. It's possible. But then we have to store them all, right? So if we order them all in one shipment, you can see that it's only going to cost us $200 to buy it, right? That's one $200 shipment. So it's bad for the shipping people, but great for us. But we're going to have to store that. So if I take 2 million and I store it, right? So let's say on average I've got a million things in the warehouse at any given time. Well, I'm going to be paying a few $100,000 just in storage costs. So that might not be good. So what I'm going to do is this. Now, we could actually go ahead and calculate the second derivative and show that that this is a minimum. So if we were to actually calculate the second derivative of this one, what would happen though is that this would actually flip, because this is a negative, this would actually flip back to a positive. And so as it turns out, we know the second derivative will be positive. I'm not going to require you to do this because, again, as I kind of said in class, if I make you do all this work just to get this number and it's not the maximum or minimum number you're looking for, why did you know what I mean? What's the point to even give you the problem? Okay, so what I'm going to do is, here's what we need to know. We need to know how many jars of orders of jars should Rock and Rob place, and how many balls should be in each shipment. So, the number of jars is 49,721. And now to get the number of orders, so this is jars. To get the number of orders, I'm going to take my 2 million, and I'm going to divide by 49,721. And it's probably not going to go in perfectly. When I just want to make sure. 2, Yep. 49721. I got approximately 40 orders. And if I back step that and do 40 times 49721, I get about 1.988 million. So it's not perfect. I'm probably going to have to place one additional order. But, given that I kind of concocted this one, I was very open to the answers you could provide. Okay, so again, the idea is this. Start with what we know. We know 200 per order. We know this is the number of orders. We know, on average, this is how many bottles will be in the warehouse. We generate a cost function based on the shipping, or we generate the cost, rather, based on the shipping cost. We figure that out. So that's shipping. And then we do the storage. Okay, we build a cost function. Now we build the cost function by adding the two costs, shipping and storage. No, there's no fixed costs here because the costs vary on how many things you're going to buy. Now we want to optimize, so we take the derivative. We set the derivative to 0 and solve. We get our critical number, 49721. Remember, we don't use the negative because there's no such thing as negative bottles. We take that number. We're going to say that's going to be our max. Again, we could use the second derivative test to show it, but if you didn't, I'm not going to nitpick that. And then you plug back in to figure out the number of orders. So in context, we need to place 40 orders per year containing 49,721 jars approximately per order. Okay, so that was definitely a long explanation. If you need any time to go back and review that, please feel free to do so. And then when you're ready, we'll go ahead and move on to the next problem. Okay, so the next of them is storing radioactive waste. So a cylindrical container for storing radioactive waste is to be constructed from lead and have a thickness of 6 inches. If the volume of the outside cylinder is 16 pi feet cubed, find the radius and height of the inner cylinder. That will result in a container of maximum storage capacity. And I gave you the hint. The volume of any cylinder is equal to the area of its base multiplied by the height. That is, since the base is a circle, pi r squared height. Okay? So basically what we need to do here is, this is a tough optimization problem, right? But we're trying to optimize the inner cylinder. So what I know is that, let's start with the inner cylinder. So the inner cylinder is equal to pi r squared height. See, based on the picture, the dimensions they're giving us. The outer cylinder, so first of all, notice how we got feet and inches. So I'm going to take the 16 inches and I'm going to convert that to 1/2 foot or 0.5 foot, because then all of the dimensions are the same. You can't mix inches and feet into the same problem. It's not going to work out. Okay, so the outer is this. So start with the so it is pi r squared h, right? It's the same idea, but it's not the same radius, right? So it's really equal to pi is pi, right? But the radius, well, look, the radius is going to be the radius of the inside, because r really means the radius of the inside, plus the additional, right? Because we want to add on. We got to add on that foot. Okay? And then the height, well, we start with the original height. We add 1/2 foot on either end. So we're really adding a total of 1 foot. In other words, h plus 1. And then we know that this in itself, that is equal to 16 pi. That's what we are given. And because we've converted to feet, everything unit-wise is going to go ahead and match up. Okay? So again, the idea is you have to optimize two variables at the same time. So essentially what we need to do is we need to use this because we need two variables. And so two variables requires two equations. We now have that, right? Inner and outer. But the thing is, remember, we need to solve for one variable in terms of the other. That's the strategy we learned. So what I'm going to do, I want to optimize the inner. So I'm going to solve, and I'm going to get h alone in the outer. And the reason I'm going to do that is because it's easier. And remember, I don't want to forget the squared. It's easier to not work with the squared stuff because we don't like to square root really. Okay? So what I'm going to do is I'm going to try to simplify this. I'm going to try to get h alone. So pi r plus 0.5 squared times h plus 1 equals 16 pi. So let's let those pi's cancel. Okay, because we can always divide by pi. Now I want to get h alone. So I'm going to divide by r plus 0.5 squared. So h plus 1 is equal to 16 over r plus 0.5 squared. And then I subtract 1. minus 1, okay? So this is our relationship for h, such that once we know r, we can figure that out, right? So remember, we've got one variable alone. This is just a little bit more complicated scenario. Now I'm going to take the h and plug it in. Now I'm on the inner, right? Because that's where we want to optimize. So pi r squared, and instead of writing h, I'm going to write this expression, r plus 0.5 squared minus 1, because that is the formula that now gives us only one letter, right? That's the goal. When you have two letters, you'd want to turn it into one. We have strategies for optimizing with two letters, but we don't have any strategies for we have strategies for optimizing with one letter, but we don't have strategies for optimizing with two. Now, since this function depends on r, I'm going to distribute the r into it, but I'm going to leave the pi out. And that's because I know I'm going to have to do a derivative. But the thing is, the pi can be taken out of the derivative, right? We can do it as a constant times the derivative because the pi doesn't depend on r. But if I don't, otherwise, I'm going to have to use the product rule, and that's going to get really messy. And I can see here, it would be the product rule and the quotient rule together. And I want to avoid that. So I'll distribute in the r squared. I'm going to use this bracket just to make things a little bit nicer. 16r squared over r plus 0.5 squared minus, remember we got to distribute to both, r squared. Okay, that's our volume just in terms of r. So what I want to essentially do now is I want to essentially take the derivative of this function because my goal is to figure out what I'm doing here. So what I got is pi times this derivative. So if I'm going to do the derivative here, let's do this one at a time. So we're going to use the quotient rule on the first piece. So we have low r plus 0.5 squared, okay, d high, so that's 32r, quotient using power rule, minus high. Now d low, so you bring down the 2, drop that to 1, and then you technically have to execute the chain rule, but the derivative of r plus 0.5 with respect to r is 1, so you could either write times 1 or you could leave it alone. It doesn't really matter, right? Because multiplying by 1 doesn't affect anything. Over r plus 0.5 squared, right? So it's to the power of 4. And then by the sum rule, this becomes minus 2r. So this is the difficult part, is taking the derivative. If you can get past the derivative, the rest is actually not that bad. Okay, so now what I want to do is I do want to do a little bit of cleaning up right here. Okay, so what I'm going to do is I'm going to do 32r times r plus 0.5 in parentheses squared. Now this, wow, this is going to be minus 32r squared because the 16 and the 2 times r plus 0.5 over r plus 0.5 to the 4th. Okay, still minus 2r. And I'll wrap the 2r in there. I just want to kind of clean things up. So what you might notice, and this happens pretty often, is that we have a GCF, right? And I guess I should be carrying my equal sign forward. So this is the derivative of the volume, right? That's what we're calculating right now. So let's take out the GCF. I'm going to actually blow my bracket out just a little bit, just so that I got a little bit more room. So notice that these both have a 32r in them. They also both have an r plus 0.5 in them. So if I factor that out, 32r, r plus 0.5, well, all that's left is r plus 0.5, right? You can imagine taking all of this and distributing it in. And then this is minus r, because all that's left in this, when you take out 32r times r plus 0.5, right, is just that r, right? You can think about distributing. The r becomes the r squared, and then everything else goes in. And this is all over r plus 0.5 to the fourth. This is not the only way to simplify. It's just one way to simplify. Okay, now, because this is all brought together, this will cancel out with one of these. Also, in the parentheses, this r and this r will cancel out. So what it is it's 32r times 0.5. So set this up again. So 32r times 0.5, which is 16r. And then on the bottom, we have r plus 0.5 to the third. Now, I want to simplify this a little bit because I want to bring everything together. So to bring this together, I'm going to multiply 2r times r plus 0.5 to the third, like this. Because remember, I want the critical numbers here. So this will help me bring everything together. Okay, so when I do that, what I get is, I know there's a lot of steps here, 16r minus 2r times r plus 0.5 to the third over r plus 0.5 to the third. Okay, now let's look for anything else we can remove from the formula here. So notice that the top and the bottom both have a 2, and we can actually take that 2 out as so. So I want to take the 2, and I want to take an r off the top. So we're going to factor that out, and what I get is 8. Okay, the 2r comes out of there. So I get minus r plus 0.5 to the third over r plus 0.5 to the third. And where I take that a step further is I can now even take that even further out, right? So what I get is my final volume is equal to, the 2r will come out, and I get 2 pi r times 8 minus r plus 0.5 cubed over r plus 0.5 cubed. Okay, so a lot of work, a lot of differentiation, but again, we isolated this, we did the quotient rule. Okay, just making sure you're very rigorous, do it step by step. Don't forget to do both things. Also, don't forget to do this. Simplified the quotient rule just step by step. Did a little simplifying. Okay, taking out some GCFs. Brought everything under one house, right, into one fraction. Took out some more GCF. Removed it. Now, you don't have to remove it. It will make it easier if you do. Because remember, our goal is to now find the critical numbers. So we need to find what makes it equal to 0. Okay. So if I'm looking at this, well, either 2 pi r is 0, possible, or the stuff in the parentheses is 0. Now, the 2 is not 0, so that's not going to be something we're going to really consider. The pi is not 0, so that's not something I'm going to consider. So basically, here's where I'm at. I need to either have r be equal to 0, but we can't really have a radius of 0. That doesn't really make sense, right? Because if r was 0, it would be 0 times, who really cares what this is? Or the stuff in the parentheses is 0, and we know the stuff in the parentheses is going to be 0 when 8 minus r plus 0.5 cubed is 0, right? Because if the top is 0, everything is 0. So in other words, 8 equals r plus 0.5 cubed, and cube rooting gives you 2 is equal to r plus 0.5, and subtracting is r is 1.5. Okay? So r is equal to 1.5 is going to be our optimal value, right? Our only other choice was 0. And now we come back and we need to do h. So here's what I'll do. I'm going to copy h. Maybe just the I'll copy h, bring it down. So since we know this about h, right, and we derived that kind of in the beginning, okay, so now what I'm going to do is I'm going to plug in 1.5, and so 1.5 plus 0.5 is 2. 2 squared is 4. 16 over 4 is 4. And 4 minus 1 is 3. So the maximum radius is 1.5 feet. The maximum height is 3 feet. Okay? So a lot went on there, but here's again what we need to think about. One, we have a relationship, volume, okay? And the volume relies on the r and the h, okay? If you look at this, if you look at the diagram, you can see that there's two variables that we don't know. So remember, whenever you have two variables, if you ever want a shot at having one unique solution, which is what we're looking for, you need to have two equations, one equation per variable. So we set up our two equations, right? So you got to know to start with that first, just like we've kind of done before, and I know this is just a more difficult application. We get one variable in terms of the other. Again, I chose h because that was easier to not have to work with the square root. I then substitute back, and remember, I'm choosing the inner because that's what I'm optimizing. So I go back to the inner, I plug in my relationship for the height, right? So that there's only one letter. I get my volume formula with just one variable, which is the goal we want because we can only differentiate right now and optimize in one variable. I take my derivative, which is going to require, first removing any constants and then using the quotient rule on the first piece and then just the power rule on the second. And remember, we're using the difference/sum rule of derivatives. I'm just calculating the derivative and simplifying. I finally get my derivative. I set it to 0. I find my critical numbers and I go from there. So I know that the optimization was definitely a long part of the test, a long part of this video. Please feel free to rewind if needed and make sure you understand this. And if you have any questions, maybe make note of those, right? And then in a moment, I'll go ahead and I'm going to move on to the last problem. All right, last problem, integration, okay? So two things we need to do. Half of us, I think, so far, and I've probably gone through a little bit more than 2/3 of the submissions. Half of us got this fully. I think the other half of us got this partially. So remember that this is an initial value problem. And so what we're doing is we are taking the indefinite integral. But when we have an indefinite integral, a constant of integration is always added on. And so I want to know a specific f of x, and to do that, the f of 0 equals 2 is going to be used to solve for the constant of integration. So what we want to integrate is e to the x minus 2x dx. Okay? And so to do that, we're just going to integrate one at a time. First, we're going to integrate e to the x dx, and then we're going to integrate 2x dx, right? And we know that there's a sum and difference rule of integrals that lets us do this. So when we integrate e to the x, well, the derivative of e to the x is e to the x, as is the integral. And the integral, or the antiderivative of 2x, is x squared. Okay, you can think about if you did the derivative of this. The derivative of e to the x, the derivative of negative x squared, negative 2x. So you can see that when you differentiate your answer, you get back what you had in the integral. So that's a way to know our answer is right. Now we add a plus c because we're dealing with an indefinite integral. And what we learned is that, well, if there had been a constant there, we wouldn't have known it because by the time we got to the integral, we've differentiated it and the constant has gone to 0. So what we do is we now know, well, look, if I make x 0, y is equal to 2. So I'm going to set it equal to 2, and I'm going to plug in 0, and I'll solve for c. So this will go away. E to the 0, as with anything to the 0, is 1. So if this is true, then that means c is equal to 1. So our final function is f of x equals e to the x. Try to make it clear. Minus x squared plus 1. So if you differentiate this, you get e to the x minus 2x, and the 1 goes away. So the derivative works. If you plug in 0, you get 1 plus 1, which is 2. So f of 0 is also 2. All right, last problem on the test, evaluate the indefinite integral. Okay, so to do this, I'm going to need to use u substitution, which I think everyone acknowledged. So let u equal 1 plus e to the x. Du is going to be the derivative of this, which is e to the x dx. Okay, observe that the e to the x dx is already baked in there, so that's a good sign. So we rewrite the integral as 1 over u du, or you could write it as du over u. Doesn't really matter, they're equivalent. I like the one on the left because it's easier to see how the integration works. Now, I wasn't too picky on this, but technically you need to write it like this. It's equal to ln. Technically, you do need to specify the absolute value, but I was pretty generous on how I graded that. Don't forget the plus c for full credit. And then you make the final substitution because you started with u's, x's, you got to end with x's. So you get ln of 1 plus e to the x plus c. All right, just using u substitution. Okay, folks, so hopefully you found this video to be helpful in terms of helping you navigate maybe where you went right, maybe where you need to improve. There will most likely be these concepts coming up later, especially on the final exam. I would expect there might be some optimization, though again, I'm going to do a lot of reflection, and I do get better, try to get better every semester. So I'm going to be thinking about the optimization as we get to the final exam. Be thinking about, though, where did we go right? Where did we go wrong? Where did my cheat sheet help me? Where could my cheat sheet help me, differently next time? As I'm pretty sure that there's likely to be a note sheet allowed on the final. All right. So just keep it up. Make sure if you got any questions, feel free to reach out to me by email or reach out to me maybe in office hours or next class. But just keep a positive attitude. Don't give up. And remember, you can do it. All right. Thanks for watching. Have a wonderful day, and I'll see you next time.